Okay, so last time we started the chapter on infinite series, right? So essentially is that I have a sequence that I have infinitely many terms, and then I just sum all the terms, okay? And then I want to see whether this sum, okay, is the limit of this sum exists, right? So essentially, as you adding more and more terms, whether it approaches a finite a constant. Okay. So, and if it exists, there is such a finite value exists, then we say that this series converges, right? So otherwise, the series diverges. So this time we are going to have some methods that help us to do some systematic tests, okay, on whether a series diverge or converge. Okay, so there are just a list of them. Okay, so and then well, some of them are easier to use, some of them are more difficult to use, and some of them are more useful, and the other are not so much. Or the other are just useful for some special cases. Okay. So let's just go through them just one by one. Okay, so the first one, okay, is known as the test for divergence. Okay, I would say this is the one that is the easiest to use, but it won't be so much useful for many of the cases. Okay, so what it says is very simple. Is that if you just take your sequence and then just look at one of the terms, okay, so a of n, and then you take that terms and then you find the limit, right? So you take the n tends to infinity, right? So, and then if you find that this a of n, just this term, okay, does not go to 0, then that is a divergent series. Okay. So example over here, right? So I have this alternating series, right? So 1 minus 1, 1 minus 1. And then you just take one of the term, right? So take the limit, right? You realize that this limit is not 0, right? So it will just be either 1 or minus 1. Okay. So then in this case, this series is divergent. Okay. So it's very easy to use, right? So just take one term and then take the limit. However, it is not a very strong test. Okay, by that I mean if you just do this test, okay, even you find that the limit is indeed 0, okay, but still it will be unnecessary, okay, but not a sufficient condition, okay, for us to say that this series actually converge. Okay. So one example over here, right? So remember last time we have this harmonic series that we know that this is divergent, right? But if you take one of the term, right, which is just 1 over n, and then take the limit, right, it does go to 0. But still, right? So this is a divergent series. Okay. So then you can see that this is a not very powerful test. Okay. So the next one is known as the integral test. Okay, so you have the picture in your lecture notes. Okay, but let me actually redraw the picture and so that I can explain what's going on step by step. Okay. So again, what I'm considering is a series, and suppose this term a of n is monotonic decreasing. Okay, so that means the n plus 1 term is always smaller than the n term. Okay. So here, let me make a graph like this. Okay, so what I'm drawing is that on the x-axis, I have the n value. So then this is 1, this is 2, this is 3, and so on. Okay. And then on the y-axis, I indicate the value of each term. Okay, so let's say here, so this is my A1, and then over here is my A2 and so on, right? So this is the A3. Okay, and then of course I'm just drawing the first 3 terms over here. So next, what I'm going to do is actually try to construct many rectangles, okay, for each of the terms. So by that I mean I'm going to take the height of a rectangle to be the value of a term. So that is, I'm going to draw my first rectangle to be like this. Okay. And then this rectangle has a width of just 1 and has a height of A1. Right. And then I'm going to draw a second rectangle over here. And you can see that the second rectangle, okay, so the height is A2 and the width is also 1. Okay. So, and then repeat the same process. Okay, the third one, the third rectangle is the height of A3 and then the width is again 1. So that is to say, the sum of this series over here is summing the area of all the infinitely many rectangles that I can draw, right? So now what I'm going to do is to construct a function. Okay, let me construct a function that passes through all these points. Okay. So a function goes like this. Okay. So my A of n is monotonic decreasing, right? So that's the function that I'm going to construct, which passes through A1, A2, A3. All the points are also a monotonic decreasing function. Okay. So that is right. So I require, so this is my y equals f of x. Okay. So the requirement is that this f of x, and then at x equals 1, the function has to be equals to a1, right? So as I draw here, and then at the f equals, as x equals 2, the function has to be equals to a2, and so on and on, right? So how do I construct this function? Actually, it's not difficult, right? So you could imagine that if your a of n is just 1 over n, right? So then you can just construct a function which is 1 over x. Then it will do the job. So and for example, right? So if my a of n is right, so 1 over n cubed, then the function that I'm going to construct is just 1 over x cubed, right? Basically, just replace the n with the x, right? So then instead of getting this discrete points, you are going to get a curve like this. So now, what I just argued, right? So in the beginning is that the sum of this series is equals to the sum of the area of all this rectangle. Okay. And we still don't know how to calculate the sum of all the rectangle, but we do know how to calculate the area under this green curve, like this function, by using integration, right? So this is my function. So then the area under this green curve, right? So of course it has to go all the way to infinity, right? So it's given by, right? So this area is given by lower limits from 1 all the way to infinity, right? So and then f of x dx. Okay. And what it really means, okay, if I write it more formally, it is this one. Right. So what does it mean by integrating up to infinity? Is meaning taking this limit. Okay. So now you can look at this graph over here. Okay, you know that this green region area, okay, will be slightly smaller than the area of all the rectangles, right? Because you can see all the extra parts that is up here above the curve, right? So that is this integral by itself has to be smaller than, or well, it could be equal to my series. Okay. So then that means if you try to do this integral and you cannot obtain a finite result, right? This integral also blow up to infinity. And you know that this series is bigger than or equals to this integral. So then that means this series must be divergent, right? So, and now, so this is help us to test whether a series is divergent. Okay. In fact, this method, the same method, can be used to help us to test whether the series is convergent. So the trick is that I'm going to shift all the rectangle to the left side by 1 unit. Shift the whole series of rectangle to the left side by 1 unit. And if you do that, what you have is that the first rectangle becomes this one, right? This purple one. So it becomes the rectangles like this, right? So now don't look at the red rectangle anymore. Just focus on the purple rectangle, right? So you can see that this purple, the sum of all these purple rectangles, okay, so will actually be smaller than the area under the curve, okay. So that is, in this case, I will have, but since I shifted all the rectangles to 1 unit to the left, right? So then this time the rectangle touch 0, okay, instead of starting from 1. So that is, this time let me write down is that, okay. This time I need to go from 0, right? And then it is greater than, actually is the same series. Right? So this time, right? So if you do the integral, right, from 0 to infinity, and you find that this is a finite value, and if it is a finite value, then that means that this series is, which is much smaller than or equals to this integral, then this series converges. Okay, however, okay, practically, we don't want to integrate from 0 to infinity, right? Because as you can see the example over here, right? If I construct this function 1 over x and 1 over x squared, you never want to integrate from 0 to infinity, right? So practically you don't. Otherwise, your integral it also does not give you a finite number, right? So that instead of doing this in the inequality, okay, so instead of doing this, okay, so what I'm going to do is just a slightly different version of it. Is that if the series that I consider, okay, go from the second term, if we go from the second term, right? So that means I only count the second rectangle and onward, right? So in this case, right, so this will be smaller than or equals to the integral from 1 to infinity, right? So this is better to use. Okay. And right, so in this case, I'm going to test, right? So this series, but this series starts from 2 instead of starting from 1. But does that matter? It doesn't matter, right? Because it's just that if you can prove that this series is convergent, then after that you add one more term back there, then this is still a convergent series. But because if you have a convergent series and then you add one finite number on it, it's still a convergent series. So therefore, okay, the summary is that, okay, you always use this integral, right? So from 1 to infinity, right? And then if this gives you a finite number, this one itself converge, then the series converges. On the other hand, if this number blows up 10 to infinity, then your series is also a divergent series. Okay. Okay, so the requirement is that, right? So the function, right? So it's decreasing. Okay, and then so that means your series is to be decreasing. Right? So if you have an increasing series, so you know that your series is most likely to be divergent anyway. Right? So let me take a look at two examples, right? So this 1 over n, right? So 1 over n, if I am going to construct a function, right? So then I just use 1 over x. And the integral of this 1 over x from 1 to infinity, right? So you have the log function, right? So then log of infinity minus 1. So this integral is infinity, right? So then this series is divergent. So second example, right? So I have this 1 divided by n squared plus 1, right? So the function I constructed, it just, as I said, is to replace this n by x, right? So 1 divided by x squared plus 1. Okay. And you try to do this integral, okay? So then you find that, so this integral is an arctangent, right? So the arctangent of infinity is actually 90 degrees, right? So pi over 2. And this arctangent 1 is 45 degrees, which is pi over 4. Then at the end, you get a finite value over here. So then this series is convergent. So, and the next test, which is called the P series test, actually this you can treat this as a special case of the integral test, because you can actually derive this result from the integral test, right? But anyway, what it says is that if I have this series, okay, 1 divided by n to the power p, right? So p is a number, right? So, and it tells you that if this converge, okay, so that means that p has to be greater than 1. And if p is greater than 1, then this one has to be converged. So if and only if. Okay. So, and as I said, right, so this is a special case of the integral test, right? So if you just construct a function for this 1 divided by n to the p, right? So then you are just doing this integral over here, right? So if you are going to do this integral over here, then you find that this is well, you know how to integrate this, right? So this is the result over here, right? So and then you'll find that if p is greater than 1, then this term, okay, so won't blow up to infinity. Okay. And of course, okay, if you do exactly p equals 1, right? So you know that this is not the correct answer. You need to have the log function, right? But for that case, also you know that is divergent, right? So then here, right? So all it tells you is that if it is greater than 1, right, drop faster than 1 over n, then it will be convergent. So I think it's good to just memorize this. It's not difficult to memorize. Right? If you cannot memorize it, you can always start from the integral test. So yet another method is known as the comparison test. Okay. So the comparison test, okay, require you to have two series, okay, in which you already know whether one of the series is convergent or not, right? And then for the other one is the one that you don't know yet and you want to test. Okay. So here, right? So given that you know a convergent series, right? So this is a series that suppose you know that it converge already. Okay. And then here, all the terms in this series is greater than 0. Okay. Then now you are going to test another series. Okay, so this is a series that you want to test. Okay. So if you look at this series and this series, okay, term by term, right? And if you realize that the absolute value of this a of n is smaller than the term m of n here for any n, right? So then you know that this series is convergent also. Right? So it's easy to understand, right? So you have something that converge, and then you have something even smaller, then of course it has to be converged. Okay. On the other hand, right? So if you know that, so this is a series that you know already is a divergent series, and then now you are going to test this series over here. Okay, so and again you do a term by term comparison. If you find that this absolute an, okay, so is always greater than or equals to dn for all n, then this series has also be diverged. Right. Again, easy to understand, right? Because this is a divergent series, and then you have something bigger, then of course that one has to be divergent as well. Right, but to use this test, right? So of course, as I said, you need to first have a known result, okay, for a series. Okay. So here, right? So as 3 examples, want to test this one, right? So this one not familiar to us, but you are familiar with this 1 over n squared. So you know that for any n, right? So this cosine square n is just between 1 and 0, right? So then this has to be smaller than or equals to 1 divided by n squared, right? For all n. And then you already know that this 1 over n squared series is a convergent series, right? So that's why this term or this series has also been convergent. And then another example over here, right? So is that I have this one over here, and then I am going to make the denominator greater, right? Instead of n fourth to the plus 7, I have this n to the 4th plus 7 times n to the 4th. Right? So n is 1, 2, 3, 4, right? So then this is 7 times n to the 4th, of course, is greater than 7. Right? So then denominator becomes bigger, right? So that means this whole term becomes smaller, right? And this one can be rewritten as 1 divided by square root of n, right? And 1 over n, you know that this is a divergent series, right? So that's why this series has to be diverged as well. So the last example over here, right? So 1 divided by n to the power log n. So this sounds complicated, but if you you know that as long as this log of n actually is a number greater than 1, right? So actually, you know that the series will be converged, right? So here I am going to consider this log n, right? So as I said, this index over here will be getting greater and greater. Right? So you can see that if n is greater than e squared, okay, so of course n has to be just integer, right? So, but you can see that then if n is greater than e squared, which is 7 point something, then the log of n will be greater than or equals to 2, right? So the smallest integer that is greater than 7.39, of course, is 8, right? So that means if you have consider n equals 8 or onwards, okay, so this power over here is greater than 2, right? So then that means this whole term here is actually smaller than this 1 over n squared. So, and this 1 over n squared will form a convergent series, right? So that's why this one is also a convergent series. Right? So what about n smaller than 8? Right? So that one is just finite number of terms, right? Those finite number of terms will just give you a finite number, right? So that won't affect the convergence or divergence of this series over here. So now another method that is known as the limit comparison test. Okay. So just now, so we are just comparing the two series term by term, right? And we want to make sure that for all n, okay, so one of the series is either always bigger than the other one, or one of the series is always smaller than the other one, right? So in order for us to say that whether it's diverge or converge. So the limit comparison test does not require us to do it term by term for all n. We just want you to take the ratio between an and bn and then look at the limit, okay, as n tends to infinity. So if you look at the limit and then you find some finite number c, okay, and that will tells you that either both series converge or both series diverge. So that is this test itself alone, okay, cannot tell you whether individually this series or this series diverge or converge. However, if you again know the behavior of one of them already, suppose I know this one, this is a convergent series, right? So and if I do this limit comparison test, then you find a finite number for the limit, then you will immediately know that the other series also converge, right? So vice versa. So over here, right? So I have these two series, okay. So and then I'm going to take the ratio, right? So between this one and this one, like here, and then I'm going to take the limit n tends to infinity. Right? So okay, here there's a typo. So this one should be 2n squared. Okay. So from this step to this step, right? So basically, I just multiply both the numerator and the denominator by this factor, and then also multiply both the numerator and the denominator by this factor. Right? Then you'll get this. And this one is equal to 1. Why is that? Okay, so it's because from this step over here, if I divide both numerator and the denominator by n cubed, okay, so what I get is 2 plus 2 times 1 over n, and then this is 2 minus 1 over n. Right. And then since n tends to infinity, this 1 over n vanishes, so then this one is equal to 1. Right. So finite number, I get finite number, and because this one, right? So we know that this is a convergent series, right? So that's why this is also a convergent series, right? So even though you don't really follow exactly the steps, right? So if you look at this series by itself, you you kind of know that this is a convergent series already, because for this one, right, so if you have n to be very large, right, so this n plus 1 will just be dominated by n, right? So if n is large enough, and also the denominator, if n is large enough, then the denominator will just dominated by the 2n cubed, right? So then you have this n divided by 2n cubed, then this goes like 1 over n squared. Okay. So another one, which is called the ratio test. Okay, so this is actually the one that we'll mostly use for the next part of this chapter. Okay, so then pay attention to this one. So this time I don't need the two series comparison, just one series by itself. Okay, and then what I'm going to do is to take the n plus 1 term, okay, and divide it by the nth term. Okay, taking this ratio, and then take the limit as n tends to infinity. So there are three possibilities. Is that this ratio, the limit of this ratio is either smaller than 1, equals 1, and greater than 1. Okay. And if it is smaller than 1, then that means this series converges. If it is greater than 1, then the series diverges. Okay. However, there's a special case here. If it is exactly equal to 1, okay, so that means this test is not conclusive. Okay, so that means this test is not give you an answer. Okay, so in that case, you need to do a different test, right? Maybe using one of the methods that I just told you. Okay. Again, three different examples. Okay, so this one, right? So I'm going to the n plus 1 term written over here, the nth term written over here. Right, so just manipulating the factors. Okay, no more other tricks involved. Okay, you see that this is the limit of 4 divided by n plus 1, and clearly this is 0. And then let me look at the third one first. Okay, that again, right? So this is the nth term, put it in the denominator, and the numerator I have the n plus 1 term. Okay, and then just eliminating or the factors, and then you find that this is equals to n plus 1, right? So and it tends to infinity as n goes to infinity, so divergent. So then the middle case, right, is actually the one that I want you to pay extra attention. Okay, is that this 1 over n squared, this time you realize that the limit is just 1, right? So this is inconclusive. So this test itself does not give you answer. But this 1 over n squared, okay, so we know that we use integral test to prove that this is convergent, right? So this is indeed a convergent series because we knew it already from previous examples. Okay, but you can see that using this ratio test alone, okay, sometimes, okay, so it cannot tell. So now this alternating series test is specially for this so-called alternating series. The alternating series is a series that has a plus term, negative term, positive term, negative term, positive term, and negative term, and so on, right? So, and this for this kind of series, okay, so if we want to test whether it converges or not, right? So we look at these three criteria. Okay. So first of all, here you see that I have this -1 and n minus 1 -1 to the power n minus 1 factor here, right? So this one itself is alternate between positive and negative. Okay. But this Bn itself, so this Bn itself, okay, so we just consider this is just always have the same sign. Okay. So in this case, right, so if it's satisfied that the Bn itself, right, so it's monotonic decreasing, right, so and it's always greater than 0, as I said, and also if the limit as n tend to infinity, the B of n is equal to 0, then this series convergent. Okay. So last lecture, right? So I actually asked the question about the alternating harmonic series, right? So you still remember this one, right? So for the harmonic series, I know that this is divergent, right? So but this so-called alternating harmonic series. So what about this, right? So this is what we are going to test right now. Okay, so is that for this one, what do you see, right? So first criteria satisfied, right? So because B of n is 1 over n, right? B of n plus 1 is 1 over n plus 1, right? And then second one also satisfies 1 over n. And the third one also satisfies, okay? 1 over n tends to infinity. As n tends to infinity, that's a 0. So that is actually the alternating harmonic series is a convergent series, okay, but not but the regular harmonic series is a divergent series. So now we have with this alternating series. Okay, so now we can talk about this concept of the so-called absolute convergence or versus this so-called conditional convergence. So absolute convergence means that if I have a series, just the sum of an, okay. So this an can be sometimes positive, sometimes negative. I don't give any restriction on that. Okay. So absolute convergence means that if you take the absolute value for the individual term and then sum them up to infinity, then and it gives you a finite number, a finite limit, then this is known as a series of this absolute convergence. Right? And if this one, right, so with all this absolute sign, if this is a convergent series, then it will also automatically imply that the series, the original series by itself is a convergent series. So, and the conditional convergence means that at this series, if I take the absolute sign for individual term and then do the sum, it does not have a limit, then it will diverge. However, if the series itself is convergent, then that's what we call conditional convergence. Okay. So what is the example, right? So the example is exactly the alternating harmonic series, right? So if I have this alternating harmonic series, where an is equals to -1 n plus n+1 times 1 over n, right? So then this is the alternating harmonic series, right? So the alternating harmonic series is something that we show already is a convergent series. However, right, so in this case, the absolute value of this an becomes it will just give you a regular harmonic series, and that one is the divergent series. So that is to say, the alternating harmonic series is conditionally convergent only. Okay. So what about absolute convergence? Right. So here, let's look at this example. So I have this series over here. Okay, you can actually see that this, because of this sign term, right? This sign of n can be sometimes positive or sometimes negative. Okay. So if I simply just take the absolute value for each term, right? So put the absolute sign out there, and then that means it's to taking the absolute sign of n, right? And the absolute sign of this sign of n, right? So it has to be smaller than or equals to 1, right? And also this denominator, if I am going to replace it with a slightly smaller number, right? Instead of n cubed plus 1, I just have the n cubed here, right? So it will have this n to the power of 3 divided by 2. Right? So that means, right? So I'm making the denominator also a little bit bigger. That means make the whole thing also a little bit. I'm sorry, I'm making the denominator a little bit smaller, and that means I'm also making the whole term a little bit bigger. So then that's why I can conclude that this series is smaller than or equals to this series over here, 1 divided by n to the power 3 divided by 2. And this is a convergent series, right? So this one is a convergent series, right? So either by the P series test or the integral test, right? So, and that's why this one converges absolutely. So one final remark over here is that suppose I have a series. Okay, so if I just multiply every term in the series, okay, by the same constant, okay, so it won't affect whether this series converges or diverges. Okay. And also, if you have this series and then if you change some of the terms, okay, finite number, okay, so finite number of the terms, and it will also won't be affecting whether this series is convergent or divergent. And the second one is that if I have two series which are both convergent, okay, and if I am going to add the two series together or subtract the two series term by term, okay, form a new series, then the resulting series will still be convergent. Okay. And the sum is just equals to, right? So adding the two sum, right? So the third one, okay, the third one I'll mention it, but it's actually the proof, okay, it will be again beyond the scope of this course, right? So, and if you look at it, it might sound a bit surprising, okay, so but I'll mention it, okay, so is that if I have an absolutely convergent series, okay, and then you have many terms, right? So if you try to rearrange the terms, right? So that means you make the second term become the first term, the first term become the second term, and so on, right? So we arrange the order, we order the term. Then it will not affect, okay, so whether the series converge or not, right? So if you start with an absolutely convergent series, you rearrange the terms, you still conclude that it's a convergent series. Okay. However, and it's still a convergent series and with the same sum, right? However, if the series itself is just a conditionally convergent series, actually, if you try to rearrange the terms, okay, so the sum that you get will be affected. Okay. What does it really mean? Okay, again, not going to dive into it deeply, but I'm just going to show you an example over here. Okay, so again, this S, okay, is the alternating harmonic series that I just talked about, right? So this series is a conditional convergent series, okay, but not the absolute convergent series. Right? We know that. So what I just said, right? So in this statement is that if I'm going to reorder or rearrange the terms, right? So something strange will happen, right? So I rearrange you can see that this series, if I rearrange the terms, I can obtain this S prime series. So what did I do? Okay, you can see that first term go to first term, second term go to second term, but then the third term here becomes the fourth term over here, and then the fourth term over here becomes the third term over here. Okay, and then here, right? So the 1 divided by 5, the fifth term actually here becomes the seventh term over here, right? And then you can see that it's 1/6 over here, 1/8 over here. You can see that I have reordered the term, right? So now, if you just focus on this green series, and then now you try to do the partial sum of the sum of the terms first, right? So the first two terms actually give you the +1/2. Okay, the third term gives you the -1/4, and the fourth and the fifth terms give you the +1/6. Okay, and then this one gives you the -1/8. You can see the pattern now, right? So you have this alternating, right? So and then this denominator every time it increased by 2. Okay, but originally it just increased by 1, right? So now if you just try to look at this red series, right, and then take the common factor out, the 1/2, okay, and then you realize that, well, you conclude that this S prime is just equals to half of the original series S. So that might sound pretty surprising, right? So you are starting with the same series, right? So but you just reorder the terms, right? At the end, right, the limit that you get, the sum that you get is actually different. So if you are for this part, okay, if you are interested to know more, okay, so you just try to look for this Riemann rearrangement theorem, okay, but I won't go into that. Okay, so this is the so before I move on to the lecture, okay, so announcement. Okay, so of course after you receive your papers, okay, so check carefully about the grading. Okay, so if there's whether the marks add up correctly and things like that. So and if you have find some mistakes, or if you have questions, okay, so about the grading, okay, so contact the TAs. Okay, so you can see here that we have 3 TAs. Okay, so each of them grade 2 questions, okay, for all of you. Okay, so that if you have some questions about a particular exam question, right, so just go to the TAs who mark that question. Okay, if you have question for question 1, then you go to Mr. Yu. Okay, if you have question for question 3, for example, go to Mr. Fong. So on. Okay, so I will upload the solution and marking scheme this afternoon. Okay, so this is one thing. Okay, so the other thing is about the final exam. Okay, so the syllabus for the final exam. Okay, pay attention to this. So again, closed book, closed notes. Okay, so these are the chapters that we will cover. Okay. Chapter 1, partial differentiation. So chapter 2 and chapter 3 won't be there. Okay, so no multiple integrations, no vector calculus. Okay, so we'll have chapter 4, differential equation. Okay, chapter 5, matrix, right, and chapter 6, the one that we are having. And chapter 6 is actually only up to part 1 and part 2. Okay, so part 1 I've just finished. Okay, part 2 is the part that I'm going to talk about. Okay, so part 3 won't be covered. Okay, So, right. So try to work hard for this. Okay. So you can see that chapter 2 and 3 are not there, right? So I would say that chapter 2 and 3 are actually the challenging part, right? So and now here we mostly, right? So majorly focus on the parts that after the midterm that are not covered in the midterm, right? So and also chapter 1. Okay. So go back to chapter 1 to do revision also. Okay, any question about the final exam? So this time, no formula sheet will be provided. Okay, so because you don't need to do this coordinate system transformation, right? So no that kind of thing, right? So that no formula for those. So here comes to the part 2 of chapter 6, and it's also the last part, right? So that will be covered in the exam. Okay. So here we are going to talk about power series and Taylor series. Okay. So they are also infinite series. Okay. So what is the definition of power series? Okay. So a power series is always written in this form over here. You can see that each term is an, which is a constant depending on n, okay, times x minus x naught to the power n. Right. So it's called a power series because you can see that the term just goes like x to the some power, right? And now this x really is a variable, right? So in some sense, right? So you can really, right? So actually treat this power series as a function, right? So because you just input your x value, and then this series, right? So if it converge, well, it will give you a number, right? So an x naught, okay, x naught is also a number, okay, is a number that we can pick, right? So but once you pick that number, right? So then it just stay here, okay? Then we don't treat that as a variable. Okay. So again, we want to investigate, okay, so whether this power series is convergent or divergent. Okay. We are mostly interested in the series that are convergent. Okay. So in the previous part of this chapter, so I showed you a number of test methods. Okay, so to test whether a series is convergent or divergent. So here, to test a power series, okay, so almost all of the time, okay, we are going to use the ratio test. Okay. So to use the ratio test, what it means is that, right, so this is the nth term, right? So to use the ratio test, you are going to take the n plus 1 term divided by the nth term, right? So then this is nothing but I just put the n plus 1 term here and term here, and then you actually eliminate the sum factors. You find that your result is that this n plus 1, okay, times this x plus 2. Okay. So you can see immediately that because of this n plus 1 term over here, as you take n tends to infinity, then this term tends to infinity. So and except, okay, except when this x is given by -2, right? Because if x is given by -2, this x plus 2 is 0. Okay. So that is, in this case, this series, okay, so is convergent, okay, only when x is equal to -2. Okay. So, and then the second case over here, right? So again, I just do the same ratio test. Okay, so you see that the result is x minus 1 divided by n plus 1. Then now, no matter what x value you take, right? So this will be a convergent series. So, and then the case 3, okay, so this case require more work. Okay, you can see, you'll see in a minute. So again, right, so start from the ratio test, right? So this part is repeated twice already, right? So then now here you can see that this time I don't have the factor n anywhere. Okay, so the n just so happened that they all cancel. Okay, as you take n tends to infinity, you see that this is x plus 1 divided by 4. So now I want this value, right, the absolute value of this to be smaller than 1, right? So in order for this series to converge, right? So if that ratio is smaller than 1, right? So it requires that the factor inside, right? So it's either smaller than 1, or greater than -1. That is, if x lies between lies between these two boundary, okay, so then you have a convergent series. However, the point that we need to re-examine, okay, are the points where when we have x equals 1 or x equals -7. Because if you have x equals 1, then this ratio is 1. Also, if you have x equals -7, then this one is -1, and the absolute of that is also 1. Right? So that is the situation when ratio test is inconclusive, right? So that is, ratio test does not help us. Then we need another test, right? So for the 2 points, so then if I just go to substitute x equals -7 back to the original series, then this is what I have, right? And now we are going to make use the other test that we have learned. Okay, so first of all, right, so this one can be simplified like this. Okay. And this is actually the alternating harmonic series again. Okay. So that's why for that, you know that this is convergent. So that is, at x equals to -7, this series is also a convergent series. So now let's look at the other case, which is x equals 1. Right? So this is 1 plus 3 in the numerator. So in that case, I have, instead of -4 to the n, I have just 4 to the n. Then this one is just a regular harmonic series. Then this time, this is the divergent series. Right. So that is, to summarize all 3 tests. Okay. So I will say that the series is convergent when x is smaller than 1, and also when it is greater than or equal to -7. Right. So this equal sign, right, so is given by this extra test over here. So now, so just one definition, just one term that I want you to be clear about is the term so-called radius of convergence, and the term so-called interval of convergence. Okay. So suppose it is found that, right, so usually by ratio test, as you saw, right, so the power series is convergent, right, for this quantity smaller than this number over here. Okay, then this R is known as the radius of convergence. Okay, if I go back to this last example over here, right, so what I have is this one smaller than 1, right, so that means it's x plus 3 smaller than 4, right, so this 4 is called the radius of convergence. Okay, so and then as you already see that at the boundary, right, so at the exact when you have x minus x naught equals to plus or minus r, okay, so and the ratio test didn't help you, and you need to test the two endpoints individually, right? So after you test the two endpoints, okay, so you will have the following 4 possible outcomes, right? So it could be adding the equal sign on one of the boundary, okay, so or adding the equal sign for both of the boundary, or none. It really depends on case by case. So then this, right, so this is just repeated what I said, right? So first ratio test, okay, find a range, and then at the two endpoints, you just take care of them individually, right? So the two endpoints when the ratio test doesn't help you. And then the 3 examples that I covered actually already covered all 3 possibilities that you can ever see. Okay, so the example 1, you saw that the series converges only at a particular value of x, and then the example 2, you see that the series converges absolutely for all x, and then finally the example 3, right, the one that we just talk about. Okay. So these are all 3 possibilities. Okay, nothing more. So in the beginning, right, so I already told you that, right, so in some sense the power series, right, so can be treated as a function, right, so because you input some value of x, and then this series give you a number, a sum, right, so it converts. So then this is what I'm saying again in this slide, right, so within the interval of convergence for a power series, okay, so this power series can be treated as a function of x. Okay. So, and one nice thing is that if you have a function that can be expressed as a power series, okay, then if you try to do differentiation or integration, okay, it's actually quite easy. Okay, it's because as long as this is a convergent series, if you try to take the derivative of the f of x, okay, it will be equals to, okay, so just taking the derivative of each term in your power series and then sum them up. Right? So that means you can just put the derivative inside the summation sign. And that means you're just taking the derivative of a polynomial, right? So infinitely long polynomial, but for sure you know how to do that. Right? On the other hand, right? So you take the antiderivative, that is if you want to integrate it, right? So you can again integrate the series term by term, and then sum them up, right? Again, right? So integrating term by term would be easy because you are just integrating this x to the n, right? So for sure you know how to do it. So, and then here, okay, just some general properties, right? So I just told you, right? So is that the power series, okay, may be differentiated or integrated term by term, right? So this is just what I told you, okay? And then after you do that, right? So actually, the differentiated or the integrated series, okay, so will have the same interval of convergence, okay, as the original series, but not necessarily for the endpoints of the interval. And also, okay, so if you have two power series, okay, so if you add them together or subtract them or multiply them together term by term, okay, so the resulting series, okay, will converge at least in the common interval of convergence. So what it means is that if I have suppose I have a first power series which converge within this range, okay, and then I have another series, okay, so which converge within, let's say, this range. Okay. Then in this case, right, so the common interval of convergence, of course, would be between 7 and 8, right? So if you add the two, right, if you do this operations, right, with these two series, right, so the resultant series will be convergent within this common interval of convergence. So at least, right, so it could be even wider than that. Okay, so but that's it will really depends on the case that you are considering. Okay. And also, okay, so the power series of a function is unique. Okay, so there is just one power series, right? So in this form, okay, so which converges to a given function. Okay. If you have learned a Taylor series before, right? So you know, actually you know how to express a function in terms of a power series. Okay. But that's what we are going to do next. Okay, so this x of n, right? I should really write this. Also, it can be also written as this also. So then let's try to express functions in terms of power series. Okay. So at this point, okay, so we are still not in the topic of Taylor series yet, right? So if you know Taylor series, you immediately know how to express a function in terms of a power series. But at this point, let's still try to just pretend that we don't know that Taylor series yet, right? So but I'm just going to show you that even in that case, right? So we will be able to find the power series of some functions, right? So this is an example. Okay, so I have this function f of x equals 1 divided by 1 minus x. Okay, and I restrict. Okay, I restrict my range of x. Okay, so to be the absolute value of x to be smaller than 1. Okay. So first of all, right, so in the last lecture, right, so I have already remind you about the geometric series, right? So actually you know that, right? So this is just a sum of this geometric series, and of course this geometric series itself is also a power series in x, right? So because of that, right? So then we are done, right? So this is the power series for this function is given by this geometric series, right? And this is unique, right? So as I told you already. So in fact, but this is just very simple, right? So but from this result, okay, so we are able to find the power series for some other functions that are related to this function. So what I am going to do is to take the derivatives on both sides, right? Take the derivative for this function, and then take the derivative for this power series term by term. Right? You know that you can do that, right? So because as long as we are within the interval of convergence, right? So you know that you're allowed to do that. Right? So that's why using this trick, right? So you are able to find the power series of 1 divided by 1 minus x to the power of n, right? So because you just keep doing derivative, you are going to keep getting more and more higher and higher order over here, right? So then because of that, you can see the power series for these functions. So then what about this one? Right. So this one is also actually related to 1 divided by 1 minus x. Okay, so what you need to do is just to replace this x by x squared, by minus x squared. Right. So if I have this result from the last slide, right, I replace this x by minus x squared, then I immediately get the power series of this 1 divided by 1 plus x squared. However, whenever we do this substitution, right, so we need to think carefully about whether the interval of convergence has changes or not, right? Because when I write down this, right, so I know that it works only for absolute value of x smaller than 1. So now that you replace x by minus x squared, then the interval of convergence for you is actually this one, right? So but no longer this one. However, luckily, right, so this time you can see that this is simply equivalent to this, right? So you can immediately see that. Okay. So now, so that means we are kind of using some clever tricks, right? So to start from this very simple result that we know, and then we try to see for more a little bit more complicated functions. Okay, how that one can be related to this simple result, and then we can obtain the power series for all these more complicated functions. Okay. So one more example, okay, is the power series of the arctangent x. Okay. So this time the trick we use is the integration. First of all, we know that this arctangent of x can be done by taking the integral of this 1 divided by 1 plus x squared. Okay. And the power series of this 1 divided by 1 plus x squared was obtained in the last example, right? So which is given here. And now we know that, right? So for this convergent power series, right? So when I do the integral, I can do it term by term, right? So that is I move the integral sign inside the summation, and then for that I'm just going to do it term by term integration. I obtain this one. So then because you are doing this indefinite integral, right? So of course you need to remember the integration constant c. So now it would be straightforward to also figure out the c, because you know that for arctangent 0, the right hand side will also have to be 0. So then that is, you obtain the power series of arctangent x. Okay, that's given by this. So here are more examples. Okay, I might not go through them one by one. Okay, so maybe I'll just leave them to you. Okay, so okay, so maybe I'll just briefly talk about. Okay, so how do I find this log of 1 plus x power series, right? So I don't know this, but I know the power series for this, right? So from previous example. And you know that if you integrate this, right, so you will get the log, right? So strictly speaking, I should say is the log of absolute value 1 plus x, right? So but we just restrict ourselves, right? So within this range anyway, right? So then this log of absolute value 1 plus x is just the log of 1 plus x. So then you know the power series of this, right? So then you do the term by term integration for the left hand side, right? So then you will be able to find the power series for log of 1 plus x. Right? So what about the other one? So this one is slightly different from this one, but if I'm just going to write it like this, I put 4 as the common factor, right? So then I have this 1 plus 3 divided by 4x squared, which is log of 4 plus log of 1 plus 3 divided by 4x squared. And this is just a number, and then this log of 1 plus something again, right? So if we know log of 1 plus x, the power series, then we just replace x with this 3 divided by 4x squared. Right? However, again, you need to be careful is that originally we know that the series only work, right? So when x is the absolute value of x is smaller than 1. So that means after we do the replacement, you need to remind yourself that the intervals of convergence becomes this, right? So then you will just be able to figure out what x should be, right? So next, what about this one? Okay, so this one, if I just have log of 1 plus x, I know what it is, right? If I just have 1 divided by 1 plus 2x, I also know what the answer should be, right? So, but what if I go to multiply them together, right? So that is, I'm going to do this. Right? And from the properties that I told you, right? So if you have two convergent series, right? So and now you can do the term by term multiplication. So that is the log of 1 plus x by itself will have a power series, right? So something plus something times x plus something times x squared and so on, right? So and then this 1 divided by 1 plus 2x, right? So also has its own power series. Again, it's something plus something times x plus something times x squared and so on, right? So then all you need to do is to do a term by term multiplication, right? So and at the end, right? So you also have an infinite series, okay? And that infinite series, okay, so will give you a product of these two functions. Okay. But again, you need to take care of this, pay attention to this interval of convergence and so on. Okay. Okay, so let me just finish this last line and I'll stop for today. Is that this is just the definition of the so-called analytic function. Okay, an analytic function, okay, is that functions, okay, if its value, okay, near x equals x naught, okay, so can be expressed as a convergence power series. Okay, so then this is called an analytic function. So and analytic functions, okay, are infinitely differentiable. So what it means is that you can always find the derivative of this function. Okay, so no matter how many times that you have already differentiated. So and this can be understood, right? So if you look at the right hand side, right? So just differentiating this term by term, right? So you can always differentiate it because there's infinitely many terms, and you can always keep differentiating it. So next time, right, so we'll talk about a very important type of power series, okay, that we use a lot, is the so-called Taylor series, right? So just now, so I told you that, okay, so analytic function, okay, so can be expressed as a power series, and of course that power series is convergent, and also that power series is unique. So then next time, right, so a Taylor series is will I'll tell you how to actually have this systematic method of finding that unique convergent power series for a function. Okay, so I will stop for today.